Well, today we're going to look at something slightly different than the course material. That heads in one particular direction. I'm going to take you a little different direction as well, and both directions will eventually end at the same place. But this will give you a little different perspective than what the course material is showing. And today we're going to lay some groundwork for what we call the definition for the definite integral. And the definite integral is the second part of calculus. We've been looking at the derivatives or differential calculus, and now we're going to start getting into the integral calculus. Now, we've already done some antiderivatives, or what sometimes we call indefinite integrals. But now we're really going to get into the integral calculus, the definite integrals, and then eventually we'll bridge that gap between the derivatives and the integrals. So first off, some of the basics, probably some slightly new notation for many of you, what we call summation notation, or possibly sometimes we call it sigma notation. We call it sigma notation because we use the Greek letter sigma, capital sigma. I don't draw sigma very well. My Greek's a little rusty, but that one's not too bad.
Is it also called?
So let's kind of get a feel for this sigma notation, and the next slide I've got it not me writing it but me typing it, so it'll look a little bit better. Here we're going to look at an example where to write out all of the terms of the summation, the sigma notation, and we're not going to worry about simplifying it. I think all of you can add. It's just I hope you can add this stuff. But it's just an illustration of what the notation means. Sometimes you'll see the sigma with the I here and then the upper number here. Other times I will write it mostly like this. Okay. But depending on how the font is, sometimes it's written like this, but what this means is we're going to have a bunch of different terms that we're going to add together, and each term is going to be in the form of something squared. And this says I goes from 1 up to 5. So to write this out, we would say, well, if I is 1, we would have 1 squared. Then plus, we are summing these values. When I is 2, our expression would be 2 squared. When I is 3, when I is 4, and finally the last term when I is 5. We stop at 5 based on this notation. So that is simply how we work with summation notation or sigma notation. Now, many times we'll start with 1, but we don't necessarily always have to start with 1. Let's see what happens on our next example. And also we sometimes use K as what we call our index. I is the most common. Sometimes we'll use J, sometimes K, sometimes N, but we have some different indices, plural for index, different letters that we use for the index. And in this case, it says going from K equal 5 to 7. And our expression is 1 over K. So to write this out, definitely don't worry about simplifying this one. To write this out, we'd have, well, our first term would be when K is 5. So 1 over K plus, then the next one up would be when K is 6, and then finally the last one when k is 7. So there would be the summation written out term by term for this notation. Questions on the summation notation? Now this next problem, we will actually be doing a lot of this, taking a sum written out kind of in the long form and writing it in sigma notation, or writing it as a summation. And what you have to look at, well, this looks like our first term, okay, then our second term, and so on, and this ends up being our last term. A lot of times we write summation notation because there's so many terms it gets really, really, really long if we wrote out every single part. So a lot of times we'll just shorten it up, and that is why the sigma notation has been created. Mathematicians aren't lazy, I keep telling you, they're efficient. We create new notations so we don't have to write out a whole bunch of stuff. So, we can start out by saying, we'll go ahead and use I for the index. I would go from where to where for what expression? Okay, so it looks like as we look term by term, what is changing on each one of these terms?
The numerator.
Okay, the numerator of our fraction. Each of them are multiplied by 7. Each term we have the plus 5 on there. And the fraction, each of the fractions has 6 in the denominator. The only thing that's changing is the numerator. So we would rewrite this in summation notation by saying 7 times what?
K over 6.
Okay, k, or whatever the index is. We've chosen I. K would be fine if you want to do that, but I over 6, and then plus 5. And then to finish it out, I goes from where to where? Okay, from 1 to 6. So this right here would be the summation notation for this long drawn out summation, even though we've simplified this one. We could have written 3, 4, 5, 3 more terms to this, but all of it kind of gets summarized into that notation. Okay? Questions there? Now, we're going to jump quickly into kind of what our definite integral will be leading up to. We're going to be approximating area under a curve over a certain interval, and we're going to end up using summation notation to describe the process of adding up or approximating this area. We're going to add up a whole bunch of easy areas to approximate the area under this curve. We'll deal with x cubed plus 1 from x equals 0 to x equals 2. Now, in looking at the instructions, there's a lot of detail here, and we'll kind of pick through it as we go. But we're to use left endpoints. Well, part A will be left endpoints, and then we'll shift, and part B will be right endpoints. I'll explain further what that means. Of each sub-interval, well, 0 to 2 is the overall interval. We're going to break 0 to 2 into smaller parts, and those will be the sub-intervals. To approximate the area above the x-axis over the given interval, 0 to 2, and under the curve given by the graph y equals f of x, in this case our x cubed plus 1, using, now we're going to break this problem into several parts. So part A is actually going to have two parts in itself. N equal 4 rectangles, and then later we'll do n equals 8 rectangles. So part A will have 4 rectangles and 8 rectangles, and then part B we'll go back and use 4 rectangles for part 1 and 8 rectangles for part 2. Now, these rectangles, we will at least make them equal width. That will make the calculations a lot easier. And then part C, after we get done with all of our work here, we're going to see kind of the results, what this is going to lead us to in finding the exact area under this curve over the given interval. So, first off, left endpoints. What does that mean? We need to first chop our interval into subintervals, and for part 1 here, we're going to chop up 0 to 2 into 4 parts. So really, we don't even need to look at the function yet. The main part of all of this is going to be separating our interval into 4 equal width parts. So if we go 4 parts, what do we need to chop it into? We go from 0 to what? Okay, 1/2, then 1/2 to 1, 1 to 1.5, or it's actually be easier to write it as 3/2 for now. And then from 3/2 to 2 would be our 4th subinterval. So we've got 1, 2, 3, 4 subintervals here. Okay. Now, let's take a look at the graph. And we'll make this really big, at least the x-axis really spread out. We're not going to be able to spread the y-axis out quite this much, but if we say here's 0 to 2, and there would be 1, and there would be our 1/2 and 3/2. Now our function, our y values, would be calculated using x cubed plus 1. Well, if x is 0, our y value is what?
0. Oh, no, it's 1.
Okay, plus 1.
Yeah.
So, okay, and we'll kind of make these a little bit smaller. So there's 1. Okay, there's going to be the point 0, 1. And then, well, let's go clear over to 2. If x is 2, we're going to be up at what? 9. So wow, I actually saved enough room. Now, where the x-axis is really spread out and the y-axis is kind of scrunched down a little bit, this will not be real symmetrical here, but we'll kind of get the idea. Oops, well, that's not. Draw it a little bit better than that. Kind of like that, maybe. Okay. Now, when I say we're going to use the left endpoints, we're going to create 4 rectangles here. And we're going to use the curve to give us the length of those rectangles, or height, if you want to think of that. So if we use the left endpoints of each subinterval, 0 will be the first left endpoint. Our first subinterval will be from 0 to 1/2. And we're going to draw a rectangle. Yeah, imagine these are straight lines. Sorry. We're going to draw a rectangle using the height f of 0 function value when x is 0. Now you can just barely see a little bit of space between the rectangle and the curve. Okay, so we're using the rectangle to approximate the area under the curve. We're going to be off by a little bit, but at least we'll get a pretty good idea what that area is going to be. So this is why I say use the left endpoint to create the rectangles. So our first rectangle would have a height of 1, or length of 1, okay, and the width, well, a little distorted here, but the width is just 1/2. Okay. So the next rectangle, left endpoint, we use 1/2. Go up to the curve f of 1/2, and then over. There's our second rectangle. Now we start to see a little more space between the top of the rectangle and underneath the curve. So we're getting a little less accuracy, but we'll see how we can get even more accuracy as we move on to the next parts of these problems. That'll be our second rectangle. So let's see, I guess we should start writing out area of the first rectangle would be what? Length times width. Length would actually be f of 0, which we already said was 1. Area of our second rectangle, well, we'll calculate this here in a little bit, but the length will be the function value when x is 1/2, and then times the width. Again, the width is going to be 1/2. Area of the third rectangle, well, again, using our left endpoints, we can draw that rectangle. And the y value will be evaluated when x is 1. And then finally, our fourth rectangle, we use 3/2 as our final left endpoint. And so length times width. Okay.
That's a lot of writing out, so I see.
Well, yeah. We're developing the idea behind the definite integral. So it's going to be a lot of writing here in these next couple days as we develop this thing. And then you will love the shortcut. Just like we saw shortcuts for the derivative definition, we're going to see a shortcut for this. But we do need to go through the long way so we kind of get a better feel for what the definite integral represents. Now, technically, we are approximating the area under this curve from 0 to 2. Now, we're using these rectangles to do that, but you can identify a little bit easier, especially these last two rectangles. We're missing this amount of area. Okay. So our approximation is going to be okay, but we're not going to be real accurate because we're not counting this area in our approximation. So let's see, I guess as we write out term by term, we can say this area will be approximated by, I'm going to go back to f of 0 instead of 1, times 1/2 plus f of 1/2 times 1/2 plus f of 1 times 1/2 plus f of 3/2 times 1/2. Now you can kind of see where this summation notation will become fairly handy. But for now, there's only 4 parts. We're going to be calculating those anyway. So summation notation won't show up yet, but when we get to the definition of the definite integral, we will see that summation notation. Notice what is happening in each term, though. Every one of them we're multiplying by 1/2. So algebraically, we could actually say f of 0 plus f of 1/2 plus f of 1 plus f of 3/2 all multiplied by the 1/2. The 1/2 is the width of each subinterval, and by making each subinterval equal width, that makes this process a lot easier.
There will be cases where that is not.
The definition of the definite integral, we don't have to have equal widths, but when we do those types of problems, we're going to make them equal widths just for our ease. So we can do whatever we want by definition, so let's make it as easy as possible. Or maybe easy is not a good word. Less difficult as possible. Okay? Yeah, efficient's a good word too. Okay. Well, let's see. We probably have enough room. Let's go ahead and calculate these. We said f of 0 was 1. F of 1/2 would be what? Let's see, 1/2 cubed is 1/8 plus 1, so 1 and 1/8. F of 1 is 2. F of 3/2, let's see, 3 cubed is 27, so 27 over 8. But don't forget plus the 1. And then times our 1/2. Let's see. We end up with what for our answer? Might help to call 27 over 8 3 3/8. Then our fractions 1/8 and 3/8 will give us 4/8 or 1/2. We've got 1 plus 1 plus 2 plus 3 plus 1. 8 and 1/2, or 8.5. Now don't forget about this thing. We're multiplying that by 1/2. So we get what?
4.25.
Okay, 4.25, and we're saying that's approximating the area under this curve. Okay, keep that in mind. We'll come back to that here in a little bit. Okay, so what we did on the previous page, that's part A, part 1. Now, part A, part 2, we would actually be separating our interval into 8 parts, 8 rectangles, rather than just 4. So we need to break our interval down into smaller subintervals. So this will be part 2, A part 2. Well, if we break it down again, we'd have from 0 to 1/4, then 1/4 to 1/2. We're essentially cutting our half width down to quarter width. And that just gives us a lot more calculations to do. 5/4, 3/2, 7/4, and 2. But as we look at this, now my graph isn't going to do this justice, but again, using left endpoints, here we'll finally start to see a little difference. If you had someone that could actually draw, that would help, especially on these first two. But Oh, nice straight lines. Okay, so there would be the 8 rectangles using equal subintervals and equal widths, left endpoints. A lot of details there. Part A was our left endpoints. So let's look at our first rectangle then. Again, with it being the left endpoints, we're going to be using x equals 0, and our width is what?
1/4.
Okay, width of 1/4 this time. Second rectangle, well, the length will be the function value at 1/4 this time. And again, times the width of 1/4. So again, we're just using area of a rectangle, length times width, but we're using the function values to create the length and making the widths equal each time. So you can kind of see the pattern that's happening here. Let's just go ahead and write out term by term here at the bottom. And we'll say the area is equal to, well, because of the equal widths, let's go ahead and factor out the 1/4. And we'd have f of 0 plus f of 1/4 plus f of 1/2, and so on. So this would be the long drawn out way of writing the length times the width, where our equal width is 1/4. We can go ahead and factor that out. And we've got f of 0 plus f of 1/4 plus on up through f of 7/4. That's going to be our last rectangle because that's our 8th one. Count up your function values. Okay. Using the left endpoints, we end up with this as our last function value.
Is there a reason why you choose to put the 1/4 on the back side?
On the back side, notation wise, you can do either. Later on, again, as we lead up to the definite integral definition, this will become a little more evident why I'm pulling it out to the back instead of out to the front.
Okay.
But at this point, it doesn't matter. So let's go ahead and calculate all these. Just pull out a calculator and we'll go with a decimal approximation. Okay, using 8 rectangles, we end up with 5.0625 as our approximation, whereas our previous approximation was 4.25. Now, we're getting a better approximation with 8, but it's still a little off. What do you think we would need to do to get even better?
Infinite.
Okay. All I'm going to have you do is go up to 8, but the more rectangles we get, the more accuracy we get.
Who figured this out?
Who figured this out? Someone very, very intelligent. Now, let's jump over to part B, and we'll skip part 1 of B and jump to part 2. Looking at, I think we can draw the right endpoints. Right endpoints actually are a little bit easier to deal with for the most part. We would be looking at, well, let's start at the right end and work our way back left. It'll be a little easier to show. This 8th rectangle, instead of using 7/4 to calculate the height, let's use 2 to calculate the height. So the rectangle here would actually be above the curve. Okay. Now, what does that mean when we compare this to the exact area? Okay, we're going to be calculating over the exact area by that much. Each rectangle will be a little bit over. So sometimes we call these overestimates, and the left side, well, it's not because it's right side or left side, but it's the way the curve is. In this case, the right endpoint will be the overestimate, the left endpoint will be the underestimate. And then it's real hard to show down here.
Could you take the overestimate and the I guess
Okay.
underestimate and find that area? Would it be more approximate?
Okay, yes, we'll talk about that here in a second. Now, as we look at part B, number 2 here, we really don't need to go back and do every single calculation. What we do need to look at, our last rectangle, we're going to be using the height at 2. Our second to the last rectangle, well, guess what? We're going to be using 7/4 to calculate that one. And the one previous to that, okay, well, do we use all of those from the left endpoints? Not quite. We'll use all of them except for what? Okay. We're not going to be using f of 0 when we're using right endpoints. We'll instead use f of 2, but everything else is the same. Okay. So f of 1/4 will actually be our first one. And then times f, or plus f of 2. And now all of that is times 1/4. To kind of work around this and make it quick to calculate, take your 5.065, subtract f of 0 times 1/4, and then add f of 2 times 1/4. And that will give you the area using the right endpoints. So you don't have to calculate 8 more function values. Okay? So what do we get when we do that? So with our right endpoints, we do get 7.0625. Now, as we said earlier, this will give us an overestimate, or sometimes we call an upper sum, and this gave us a lower sum, the 5.0625. So what could we say about the exact area?
Probably an average of the 2.
Well, the exact area, and this is part C, based on the results of your work, give an upper bound and a lower bound, or a range of values that represents the best approximation of the exact area under the given curve. So that exact area is going to be in between 5.0625 and 7.0625. Now, we have actually narrowed in on the exact area pretty good, even though we only used 8 rectangles. And like we said, to get even more accuracy, we're going to be using more and more and more rectangles. And ultimately, this leads us to the definition of the definite integral. We theoretically consider how many rectangles? we will be looking at number of rectangles approaching infinity to be able to give us the exact area. Okay, so that's what we're shooting for. And this worksheet for today, summation and approximating area, gives you kind of some of the basic notation and operations we'll be using in working with the definition.